So let's talk about surface area of a cone. In the last episode or topic, we covered the volume of the cone. Surface area is a different topic within that, but let's cover this separately and let's talk about that. So we already know from the previous episodes on cylinder and other 3D objects like cuboid, there are two kind of surface areas whenever we talk about a 3D object. One will be the lateral surface area and one will be the total surface area. When I say lateral means what is the surface area on the sides of it, just calculating the sides without any bottom and top. So that's in this case, since cone or cylinder are curved around the lateral sides, it's also called as the curved surface area, just the curvature part of it, not the bottom part of it. So this, the whole green part, what is the area of this part? Okay, that's the curved surface area, not including the bottom. And another concept is total surface area or whole surface area, which means that you should also include the bottom of it. Let's say if this was closed by a lid which was circular in shape, this part at the bottom which is circular, if I have closed this completely using the circular shape, that would also have an area. So what is the area of that? So in that case, you add this area, curved surface area, plus the area at the bottom, and that will give you the whole surface area or total surface area, whatever you want to call. That's the concept of surface area. Anyway, so before we do that, in the case of cone, we just need to do a quick refresher on what is a circle and what is the area of a sector. Okay, let's do a quick refresher. And I think I've also covered this topic under the 2D object of mensuration under circle. I will also covered this, but let's talk about this in a minute. Okay, so over here, if you see, let's take this circle. Okay, let's take this circle. And as you visualize that this green portion I'm cutting out, okay, I'm taking a scissor and completely cutting it out, okay, this green portion, okay. So this green portion is almost 1/4 of a circle. That means if you take this as a quadrant, so this is the first quadrant, this is second, this is third, and this is fourth. So almost one quadrant, exactly 90 degrees, I'm removing it. Exactly 90 degrees, I'm removing it. That is almost 25%, not almost 25%, or 1/4 of the circle I'm removing, okay, from this. And the remaining thing is just going to be this 3/3 of this circle, okay, this 3/3 piece, whatever I'm highlighting, that's the thing that is only remaining, okay. So in that case, what happens is this whole circle is chopped into two pieces. This forms, let me just erase it out. There are two sectors that are formed. One is the minor sector and one is the major sector, or you can call as arc also. So this part in all the way from here, if you see, this is the bigger arc or bigger sector after you chop. And this part, let me take a different color code here. Let me take this lavender or purple. This part over here, since you're cutting out this whole green portion, this part is the smaller arc or the smaller sector. So we're not going to be worried about that. Let's focus on the bigger sector because this part is already cut out. So we're not going to worry about that. Okay. So now, or if you even take this diagram, and in this case, I'm just cutting at 90 degrees for just explaining a concept to you so that it forms an even quadrant or it's exactly 90 degrees and we can get 1/4 of the circle. But you can cut down at any point, doesn't matter. Here is the whole circle and this is not 90 degrees, but you're just cutting from this point to this point and you're cutting this whole piece out. And again, it's going to form in two sectors. This is a bigger sector or bigger arc and this is a smaller arc. That's what it said. Okay. So now let's see what's going on here. What happens when we do it? What are the observations? So when we do this, what we see is the area of the circle, right? The whole area of the circle is given by area is equal to 2 pi r. We know that, okay? And circumference of a circle is, area is, I think I messed up here. Just give me a second, excuse me. All right, area of a circle is equal to pi r square, okay? And circumference is 2 pi r of a circle. We know that. That means both of them are dependent on the radius for its own length. That means we can say that area is proportional to circumference or circumference is proportional to the area, which means if you increase one of this, the other is going to increase. If you decrease one of this, the other is going to decrease. That's the relationship that they have, okay? And that's what I have kind of put here, okay? So bigger the area, bigger the circumference and vice versa. Similarly, in the construct of a sector also, the sector is nothing but a chopped portion of the circle. This concept is still going to apply, right? If you take the area of the sector in the orange color, this area of sector, this is not a whole circle, but it starts from here and stops here. This area of the sector also is going to have the same characteristic where it's going to be proportional In this case, it's not the whole circumference, but this whole piece is called as arc length, length of the sector. So it's called as arc length or length of the major sector or major length of the major arc. Okay, arc length or length of the arc. So instead of circumference, the same concept applies, but this area of sector is going to be proportional to the corresponding length of the arc that it owns. Okay, because the remaining portion is removed. Okay, same way if you see, it's going to be this particular major arc. Okay, the length of this arc is going to be proportional to this area of this whole sector, whatever is remaining, right? That's what it is. That means that's what we get in red. Okay, area of the length of the sector proportional to the area of the bigger sector, and circumference of the whole circle, which we saw in that case, that will be proportional to the whole area of the circle. Okay, and you can think about the circumference as the whole arc length, complete 360 degrees. That's what we're talking about. Okay, so if I take these two equations, that means I can comfortably divide it, because the ratio is going to be the same, because we're talking about length of a portion is going to be the proportional to the area of that portion. That means the arc length, area of the sector, is going to be, the ratio of the arc length divided by the whole circle, circumference, the ratio of that is going to be equal to the area of the specific sector divided by the whole area. That's what this means. These two lines, if I take the ratio of that, the proportional item goes away and it replaces by equal, because the ratio is going to be equal. Okay, that's what it means. And this is how you're going to calculate, since what is the relevance to this topic. If you see here, sector area is nothing but whatever is remaining. We are interested in that area of that. Okay, and because we're going to cover that in the cone, and we'll see that cone is nothing but a sector of a circle only. So to calculate the area of that, which is what we're talking about, right, the curved surface area, the first one, we will apply this formula, okay, to calculate the area of the sector. And that's the relevance to this topic. So you just remember this equation of how the length and circumference are related to the respective areas, and this formula we will use to calculate the area of the specific sector, and hence the cone, in the next topic.